Welcome back to our Advanced Instabase Flow series. In our previous video, we introduced the concept of user-defined functions, or UDFs. Today, we're diving into the structural differences and core use cases of our two main workhorses, the map UDF and the reduce UDF. The difference between these two hooks lies entirely in how they handle execution scale. Use a map UDF when your custom processing logic operates on a single document, running across every input record in parallel to maximize throughput. Let's look at the mechanics of a map UDF under the hood. When a map UDF executes within your pipeline, it receives a primary input dictionary called input_record. This payload contains critical document metadata, including the file path of the input document, the raw content formatted as a string, and the desired output file name. This design ensures that each document is processed independently and in isolation, allowing you to easily read runtime variables, call external APIs, or perform character-level sanitization on a per-file basis. Let's walk through the actual Python implementation for our map UDF as shown in our script. Our function, map_UDF_func, is registered using the standard register_fn decorator with provenance set to false. Inside the function, we unpack our input metadata by extracting the input file path, the raw file content from the content key, and the original output file name directly from our input_record dictionary. Next, to copy our underlying extraction document format, we invoke our helper function, get_output_ibms. This utility takes our input file path, the target step folder, and our file content to safely copy the process document representation. Finally, we construct our return payload. A map function must always return a dictionary containing an out_files array. Here, we define our target file name dynamically by prepending map_UDF to our output file name, and we pass our copied output message representation directly as the file content. Now, let's explore the reduce UDF step. Dragging the reduce node onto our canvas allows us to run serial processing across our entire dataset. Instead of receiving a single record, a reduce step is passed input_records as a Python generator, enabling us to aggregate data across all processed files. Inside our reduce function, your script uses a standard for loop to iterate over the input_records generator, pulling out individual record contents as the loop runs. A classic example of a reduce UDF is compiling a single consolidated summary JSON file of our entire run. Inside the loop, we use the parsed IBOCR builder utility to load each record's extraction details, pulling the specific fields we want from get_refined_ phrases, and compiling them into a central collection. Once the loop finishes processing every document in the batch, we then leverage the client's .ibfile file system interface to write our unified summary file directly to our root output folder. This ensures that even if you process hundreds of documents, the final step yields a single, highly structured summary file. No matter which UDF type you write, your Python file must include a standard register decorator. The register_fn decorator takes a key named provenance, enabling the flow runner to dynamically discover your code. Back on our canvas, we map our steps. For our parallel map node, we invoke our function using the cell formula map_UDF_func, input_record, step_folder. For our reduce node, we reference our summary function and we can call the function directly like generate_summary_reduce_func. To summarize, map UDF's process files in parallel, receive a single input_record dictionary, and output individual files to downstream steps. Reduce UDF's process batches in serial, loop through an input_records generator, and are typically used to write consolidated reports or run cross-document validation checks. Choosing the correct architecture ensures your custom pipeline scales efficiently, regardless of your document volumes. In our next session, we'll move beyond record processing to explore flow lifecycle events. We'll show you how to write pre-flow and post-flow UDFs to coordinate environmental setup and push your finalized database exports to external systems. Thank you for watching.